Hey guys, it's your favorite environmental science teacher, and we're going to be moving on to Unit 6. So, Unit 6 is going to be focused on energy. So we're going to look initially at what energy is, how we can measure it, and then we're going to get into the specifics of renewable and non-renewable energy. And it's going to go into a lot of detail, talking about all the different types and how they're used. All right. So, for those of you that took AP Physics last year, and I know physics can be a bad word, but this should be just a little bit of a review for you, okay? So, when we talk about energy, what we want to know is how much work is able to be done with energy, okay? So, let's go ahead and write down what the definition of energy is. So energy is the ability to do work. Okay? Now, what is significance, especially when we're looking at it from an environmental point of view, is quality. Okay? Quality. How well is it working? Okay? When we look at how well is it working, the question that we ask ourselves, is it organized? Now, you're probably wondering, well, how can energy be organized? Well, basically we're looking for a massive punch of power. We're not looking for something that takes a long time to work. We want something that's going to be very efficient and as fast as possible. Okay, so when we look at this picture right here, it's showing the difference between high quality and low quality energy. So the lowest quality is going to be when we have temperature. Now, heat is a type of energy. Heat does have the ability to do work. Sorry guys, I got a little pop-up right here. Okay, heat has the ability to do work. Now the problem is heat is not the greatest way to have energy. Okay, so anything that is low temperature, we say this is disorganized, meaning it has very low quality. It's not able to do a really great job of getting us energy. Now, when you have the temperature increase, it becomes more organized, but it's still not high quality. Okay, so this is where we see things like oil, coal, natural gas. Okay, so these are going to be our non-renewable energy sources. So these are non-renewable. Now, when we get up here to the highest quality, this is where it is going to be the most organized. This is what we want. Okay, mechanical energy, electricity, both of those are going to be very high quality forms of energy. Now, this is where things are going to start to come together, is electricity and mechanical energy can come from the burning of those non-renewable resources, but they can also come from renewable resources like sun and wind and water. Okay, if we're just solely using the oil, the coal, the natural gas for energy and not converting it into electricity, then it's still going to be a lower quality energy. Okay, so let's look at thermodynamics. So this is where that little bit of physics comes in. Okay, so thermodynamics attempts to explain how energy is used and what happens to it when we use it. So, the first and second law of thermodynamics explain how energy works in two different ways. Okay? And energy does both of these. It's not a one or the other. Okay? So, the first law of thermodynamics, it states that energy is neither created nor destroyed, but is simply converted from one form to another. Now, that's the textbook definition. Okay? Let's go ahead and write down the textbook definition. So it says that energy is neither created nor destroyed. It is simply converted from one form to another. That is what I learned in college. That's the definition I learned. I don't know how I remember that from college, but it's just one of those weird things that stuck in my head. Okay, so what does this actually mean? Let's use photosynthesis as an example, okay? In this, we are going to have some type of energy transformation. So what does the energy look like before, and what does it look like after? Okay, so photosynthesis. Let's look at photosynthesis. Now, in photosynthesis, what is the ultimate source of energy? Where does energy begin? What does it look like? If you said light energy, you're correct. So we start off with light energy. Now, when light energy is used, that's before, what is it converted into after? Think about the plant. What is the plant using light to produce? And that's going to be our glucose or chemical energy. Okay? Now, that is the first law of thermodynamics. What does it look like before? What does it look like after? And it's going to be converted. Okay? We're not creating the sun. We're not destroying the sun. We're simply converting that light into another form. Okay? Now, the second law of thermodynamics also has to do with energy transformation, but it attempts to explain what happens to some of that energy after it's used. Okay, not converted, what is happening to it after it's used. So let's write down the textbook definition for the second law of thermodynamics. So, the second law says, oh, sorry guys, when energy is changed, from one form to another, some energy is lost as heat. That should ring a bell. That should sound familiar to you. Some of this is lost as heat. Well, where have we learned this before? Food chains. Yep, food chains. Okay, so our example here, the second law, is going to be food chains. Okay, it's also, as we'll see here in a second, usage of non-renewable energy. We'll get to that in the next video. Okay, all right, so energy before, energy after. So this unusable energy right here, guess what this is? Heat. Yep, that is what escapes into the environment. Okay, so let's look at an example right here. This is the second law of thermodynamics. All right, so we have solar energy. This is converted into chemical energy. Guess what? That's the first law, right? The chemical energy is converted into food for the plant. That's also the first law of thermodynamics. Okay, chemical energy can then be transferred into mechanical energy. That's also the first law. Okay, now what's coming out of this? This is the waste. This is the second law. There's more waste. There's the second law. More waste, second law, and again, more waste. Second law. Guess what, guys? This waste heat, as we just mentioned above, this is low quality energy. So the heat that escapes is low quality. Okay? All right. Now, let's look at the next page. Now, this page is talking about what we call feedback loops. Okay? Feedback loops is the response to change. All right? And this is specifically in the environment. Now, your body has its own set of feedback loops, but this is not anatomy and physiology. We're looking specifically at the environment. Okay? So, we have positive and negative feedback loops. So the first one we're going to look at is what is called positive feedback. All right. Positive feedback. So, in a positive feedback loop, the system changes further in the same direction. Okay, so let's look at an example. This is our example of positive feedback right here. Okay, we just learned in our agriculture unit that it is important to have grass, trees, any type of plant life to prevent erosion of the soil. Okay, erosion of soil means we can't grow things, so it's going to decrease plant cover, agriculture production, etc. All right, so in this situation, we have decreasing vegetation in the first step. Okay, when you have decreasing vegetation, what does that cause? It causes an increase in erosion. Okay, so if you have decreasing vegetation and increase in erosion, what's happening here? Look at this picture. Look at this picture compared to this one. What's happening? The erosion is causing less vegetation to grow. So the vegetation growth leads to, right here, or the vegetation loss leads to erosion and nutrient loss. Well, guess what that causes? More plants to die. Okay, right here. More vegetation dies. And guess what? It keeps going and going and going. So what's happened right here? We've got a lot of plant death. So in a positive feedback loop, the situation just keeps getting worse. It can't correct itself. So there is no self-correction. The problem worsens. Hopefully that makes sense to you guys. Okay. With the negative feedback loop, this is negative. Okay. The system changes in direction. So think about your thermostat. When your thermostat is set to 70 and it's hits 70, it shuts off. Okay, so it corrects itself. All right, guys. I will be posting some practice work on positive and negative feedback loops.